Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Find the green triangle area in the rectangle. Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Start with rectangle IBCD, corners taken in order. Point E rests on the top side, AD, and point F rests on the right side, AB. Three segments, segment EF, segment FC, and segment EC, are drawn across the inside. Those three segments slice the rectangle into exactly 4 triangles. 3 hug the corners at A, at B, and at D, while the fourth triangle, EFC, sits in the middle. Together, they tile the whole rectangle with no gaps and no overlap, and that tiling is the key idea. Because ABCD is a rectangle, the angles at A, at B, and at D are each 90 degrees. So every corner triangle is right-angled, and its area is 1/2 the product of the 2 edge lengths meeting at that corner. That fact turns each corner into a clean equation. The amber corner triangle EAF has area 4. Its legs are segment AE running left along the top and segment AF running down the right side, meeting at the right angle at A. Hold on to that value 4. The blue corner triangle FBC has area 5. Its legs are segment FB along the right side and segment BC running left along the bottom edge, meeting at the right angle at B. That value 5 is the second clue. The rose corner triangle CDE has area 9. Its legs are segment DC along the left side and segment DE running right along the top edge, meeting at the right angle at D. Now all 3 corner numbers are in hand, 4, 5, and 9. The green triangle EFC in the middle is the piece we want. It is the only one of the 4 without a number yet, so everything now aims at pinning it down. Areas of non-overlapping pieces add up to the whole. So the rectangle equals 4 plus 5 plus 9 plus the green triangle. The 3 corners already total 18, so the whole rectangle is 18 plus the green piece. Rearranging, the green triangle is the rectangle area minus 18, so the whole problem reduces to one missing number, the area of the rectangle itself. Let us go find it. Give the rectangle width A down the right side and height B along the top, so its area is A times B. Call that unknown area X. Finding X is now the whole game. Let segment AF equal P along the right side and segment AE equal Q along the top. These 2 short lengths, together with A and B, control all 3 corner triangles, so they are all we need to track. The leftover right piece segment FB is the full width minus P, that is A minus P. The leftover top piece segment DE is the full height minus Q, that is B minus Q. Now every leg of every corner triangle has a name. Write the amber corner as an equation. Triangle EAF has legs P and Q, so 1/2 PQ equals 4. This is the first of our 3 area equations. Multiply both sides by 2 to clear the fraction. That gives PQ equals 8. Keep this product handy. It will slot into the final step. Now the blue corner. Triangle FBC has legs A minus P and B, so 1/2 of A minus P times B equals 5. This is our second area equation. Multiply by 2 to get A minus P times B equals 10, then distribute the B. That gives a B minus PB equals 10. Notice a B is exactly our rectangle area X. Replace a B with X, so X minus PB equals 10. Solve for the product PB, giving PB equals X minus 10. One clean expression ready to be multiplied later. Now the rose corner. Triangle CDE has legs A and B minus Q, so 1/2 times B minus Q equals 9. This is the third and last area equation. Multiply by 2 to get A times B minus Q equals 18, then distribute the A. That gives a B minus AQ equals 18, and again, a B is the area X. Replace a B with X. So X minus a Q equals 18. Solving gives a Q equals X minus 18. Now we hold three tidy facts. PQ is 8, PB is X minus 10, and a Q is X minus 18. Our first insight is this: multiply paired equations to eliminate the cut positions. Now substitute what we know. The product PQ is 8, and a B is X, so the left side is simply 8 times X. The unknowns P, Q, A, and B have collapsed into one term. But the same product also equals X minus 10 times X minus 18, using the blue and rose expressions directly. Setting the two forms equal gives X minus 10 times X minus 18 equals 8X. A single equation in the single unknown X. Expand the left side. X times X is X squared. The cross terms are minus 18X and minus 10X. And 10 times 18 is 180. Collecting the middle terms gives X squared minus 28X plus 180 equals 8X. Subtract 8X from both sides so everything sits on the left. Minus 28X minus 8X is minus 36X, leaving X squared minus 36X plus 180 equals 0. A clean quadratic in X. A second insight now finishes the structure. Only the geometrically possible root survives. Check the two roots against the geometry. If X were 6, then PB would be 6 minus 10, a negative length, which is impossible. So 6 is rejected, and the rectangle area must be 30. As a sanity check, a rectangle 6 wide and 5 tall with area 30 fits perfectly. Take segment AF equal to 4 and segment AE equal to 2. Then the corners are 1/2 2 times 4 is 4, 1/2 2 times 5 is 5, and 1/2 6 times 3 is 9, exactly the given numbers. Now finish the original goal. The green triangle is the rectangle minus the three corners. 30 minus 4 minus 5 minus 9 removes 18 and leaves 12. So the answer is 12. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.